All right, and on that note, let's start. So we are going to start the first video in a series of videos about path integration. We're going to use quantum field theory by Srednicki, and quantum field theory by Srednicki has a nice treatment of path integration, starting with quantum mechanics. We're going to start with that. If you would like to follow along, I put the notes on Discord. You may join Discord by typing in !Discord, and then I will, and you can go to the path integration notes and find the notes there if you'd like to follow along. All right, so we are going to start. We're going to be in chapter 6 of Srednicki. I'll put my microphone down here. And like I said, hopefully the mic issues will be fixed by Friday. Or not fixed, but they'll be better. Improvement. We always want more improvement. Now, the other thing is, if you have a question, !ask, and then your question in the chat, and it will go to a queue that my mods will happily take care of until I get done with the chalkboard. Or if anybody just wants to answer it, we do have lots of very intelligent people in chat who can answer these questions. All right, so let's begin. I'm gonna turn this up just a hair. It's up pretty loud right now. Hopefully it's loud enough for you to hear me. And not too loud to be crushing. Okay, so let's begin our path integrals.
Yes, you're loud.
Like too loud, or? All right, so, and I will be checking chat. I have chat on my
No, it's good.
Okay, good. So if you are a sub and want to use text-to-speech, then that would be best to ask questions, but if not, then just write them in chat and I'll catch them when I do. And if it's, but always do !ask so that, in chat, so that way it does go somewhere if I'm not looking. Okay. All right, so today we're gonna be doing path integrals in quantum mechanics. We're gonna start this. There's gonna be probably two days devoted to path integration in quantum mechanics. And then we will eventually make that go into quantum field theory. I'm going to shut my garage door. And I will open that again when we're done with this, but for now I want to keep it closed. Okay, so the best thing to do is to start with the non-relativistic Hamiltonian. So if you take quantum mechanics or any type of if you've taken quantum mechanics, you've dealt a lot with the quantum mechanical Hamiltonian, where you have operators P and Q, and you know what all of those are. So I am expecting you to have some sort of background on quantum mechanics, but if you don't, that is no biggie. Just I will try to explain them the best I can as I go. So let's start with the non-relativistic Hamiltonian. There's a general form, which is, we're just going to run it with this. 1 over 2m times the operator p squared plus v operator q. Now, this p is just momentum, as a momentum operator, and this q is a position momentum, or position operator. And this is the Hamiltonian, so this is the addition of all the energy. So we can say this is kinetic energy, and this V is for potential, so this is the potential energy term. And this is just kind of a general Hamiltonian that we see a lot in quantum mechanics. So we're gonna want a couple things to be true. We're gonna have h bar equal to 1, and we're also gonna want P and Q, the commutator of P and Q, to be equal to I. And that's just for clarity's sake and convenience sake, if anybody's interested in knowing that, it's there. So what is our goal? Our goal for today, or our goal maybe for today and tomorrow, or next Wednesday. Our goal is going to be to evaluate a probability amplitude. For the particle to start at position Q prime at, at some time T prime and end at position Q double prime at T double prime. Now, what does this look like? Well, there's going to be some probability that we're going to have a particle that starts here and ends here. So here we'll call this Q prime, T prime, and here we'll call this Q double prime, T double prime. So again, these are two dimensions. Alright, so it's good. We're talking about in two dimensions. We have a position and a time here, and a position and a time here. H bar equals C equals G equals E equals pi equals 1. Very good. Okay, so, alright, so this is the goal. We're going to try to figure out the probability that you're going to start here, and all this stuff in the middle is fuzzy. We don't understand it yet. But we're going to work on understanding it. So we can express this amplitude very straightforward. The following way, we're going to express the amplitude like this. And this is one thing that's going to stick with us for a while. This type of notation, where we have our final state, we have our Hamiltonian. Now this is the Schrödinger picture, but we're going to turn it into the Heisenberg picture next. That's the goal. Q prime. Now, this is just going to be, we apply this, and really when you do this, you exponent, or you do a Taylor series, and you apply the H to the Q, and then you get the eigenvalues, then you take the Taylor series again back into the exponential. If you've done all of quantum mechanics, you know what that means. If you don't, it's not necessary. Just imagine that this is the final state, this is the initial state, and this thing is going to tell us how a particle is going to move around in the middle. But we don't really know a lot about it. We have to do more to this before we can actually evaluate how the particle is moving. So one way we're going to do this is we're going to try to change this into the Heisenberg picture. So the Heisenberg picture is one where the operators depend on time. So in the Heisenberg picture, we're going to have, and we're going to write it as a time-dependent Q, which can be expressed as a time-independent version of itself via like the old, the time evolution operators and whatnot that you have seen a million times if you, like I said, if you've done quantum mechanics. And if you don't remember this, or you are new to this, just say that like this Q, it depends on time, like it changes on time, and this Q we can consider instantaneous while this stuff is changing around how it behaves in time. Okay. Now, well then we can say a couple things about it, right? We can say that the instantaneous Q of t acting on a state, QT, like me, is it primed? It's not primed. QT is then equal to some instantaneous eigenvalue Q, like some instantaneous space. It's basically saying where it is in space, times the state again, right? And that's it. That's just to tell you how it behaves instantaneously as it acts on that. So there's a couple other things we can say, like what does this actually look like? And let me make sure I don't go into the chat window. So let's box this. And then I have about that much room to work. Okay, cool. And then we have, the state qt is equal to e to the I h t times q. And again, it's the same thing. Remember how I said that this was the instantaneous q and this is operator, that is. And this is how it behaved, the time it's supposed to behave around it. And the same thing is going on here. We can take the t state out and just put it into the exponent, and it works for this particular case, okay? And another thing we could write, and this is about as far as I can go down, I think, assuming you guys can all see. And then we can actually take this to say, well, that just means that this is, we can rewrite this as the, if we were to apply this operator to q, we can get some eigenvalue q on this eigenstate q. Oh yeah, look at that, I'm just above Jen. Awesome. QT is a QT. Yes, it is. Now, this is all just laying out the groundwork, telling you sort of like what Q and P do. We haven't actually done too much with it. Again, this amplitude right here is the thing that we're going to have to keep going back to. And this is the thing that tells you if you want to start here and end here, then this is the stuff that's going to happen in the middle. But we don't really know what that stuff is. We can take a look at some of this stuff and sort of explain that what Q looks like instantaneously, and then we can say how this stuff, again, still holds the key to what's inside here. So we need to actually get there. So, let's erase this, and, oh, I should say one more thing before I erase it. All of this stuff means that we can then write the amplitude right here as, in the Heisenberg picture, as the amplitude just being final state and initial state. And this, if you've done any particle physics, this is really a lot of what you see when you consider initial states and final states. You see something that looks like that. So now we're going to use this in the Heisenberg picture, and this will be our final version of what the amplitude notation should look like. And then from now on, we're going to be trying to figure out what that means. So, let's erase this. CPT asks how you define expression like, oh, I see. How do you define expressions like the exponential of negative I h bar t? Do you need an h hat to be diagonalized? You don't. It can be diagonalized usually, or else it doesn't have real eigenvalues, I think. But it doesn't necessarily need to be diagonalized, no. It's just about how it's going to behave. Now, ours behaves very nicely, right? We have P and Q. They're in separate things. P is quadratic and Q is linear, or so it seems. I guess it's some function of Q, so it really could be whatever you want. But P is quadratic, and they're in separate terms. So that makes it kind of nice for us. So alright, so let's keep going. So now what we're going to do is, instead of trying to evaluate this whole thing, we'll split this into little chunks, little sections like this, in the dimension of time, okay? So we know that it's going to start here and end here. We're just going to say that. We're going to say that, t double prime is larger than t prime. That's something that we can say by convention. The same way we could say that t prime is larger than t double prime and it's going this way. It doesn't matter which way it's going, back or forth. We just say which way we're going to evaluate it. And we're going to divide. We'll say that t is going to be the time difference between the two, right? And we're going to divide it into n equal pieces. Oh, n plus 1, excuse me. Pigeonhole principle. Divide an n plus 1 equal pieces. And that just means that we can now define one of those little individual pieces as the time difference divided by n plus 1. That's how big each of those are. So if we wanted to say that this is that this is a continuous system, all we got to do is take this dt, this delta t, and send it to 0, and then it's going to be continuous. All right. So let's So this actually gives a complete set of position eigenstates, right? Which is the things that we're going to talk about. So we can rewrite our amplitude. I'm going to start over here to make sure I have lots of room. So we can rewrite our amplitude now as the integral, the product, j equals 1 to n of d qj q double prime e to the negative I h delta t, because now each of those original ones that I remember how I said that this was going to be like the final, what happens in the middle, and then the initial. Well, now we're just going to be taking each of these individual pieces, and we're going to be like, what's the particle look like as it goes from here to here, from here to here, from here to here, from here to here, from here to here. And we're going to integrate over the whole thing so that we know exactly how the particle moves throughout the path. Now, like I said, this path is arbitrary. This could be a path, this could be a path, this could be a path, this could be a path. They could all be different paths. It doesn't matter which one. We're just going to take whatever path we want and just split it into n's. So then we're going to add all of the states, and we're going to add basically, like, if we integrate over the whole thing, then it should look like, we should actually know how it moves. All the way down to q1, e to the negative I h bar delta t q prime. So now, like I said, we're going to start here. Well, actually, we're technically starting from right to left. But we're starting at q prime, and we're seeing how it behaves as it moves on each of these pieces. And this delta t, again, we're going to eventually want to take down to 0 Heisenberg. Welcome, welcome, welcome.
Can you go over what the symbols are again?
Which symbols? So this value does not depend on your choice of path. No, not at all. And the reason being is because n is arbitrary, right? So it doesn't matter if I break this one into n paths, this one into n paths, this one into n paths, this one into n chunks. I should say chunks, not paths. This one into n chunks, this one into n chunks. It doesn't matter, just to change the n appropriate to whatever path it is. After the integral. Oh yeah, so this is the integral. This is the multiplication sign. So you're multiplying. It's like the same thing as the sum over. And this is just multiply over. So sorry, I took that for granted. And then the dq is the integration variable, dqj, and then you are just going to integrate over every single one of these. So you get one dq for every single one of these states. And then you're just multiplying them all together, and you're integrating over the whole thing to kind of see what's happening over each chunk of time. But this is just the amplitude that it's going to go from this last chunk to the final stage, or the second to last. And this one will be the one before it.
Why the product?
Completeness theorem. Let's write the completeness theorem up here so we have it. I'm adding a bunch of these. dq, j, qj. I can multiply by 1 no matter how many times I want, right? It's equal to 1. I can't add that. I can't add 1. But I can multiply by 1 how many ever times I want. So I'm literally just inserting these every so often. Lauren, did you have a question or didn't even see it? Saying hi is not an interruption.
Got
I
you.
love when people go. I love when people pop in. QS are going to be the eigenstates. It's basically just going to be the energy that for the particle to be in this spot, this spot, this spot. All the energies for the particles to be in each state. So the state being the position that it's in. So these are position eigenstates. Oh, you hydrated me. I'm sorry. I'm missing some of the things because my phone doesn't show them. But I am parched. So it's a good reminder. All right. So this is where we're at so far. This guy's good. Now we can consider one amplitude. So let's just take out one amplitude and take a look at it. So let's take the amplitude from Q2, E minus I I, H, and these are all supposed to be H hats because they're
Avoid
operators.
heavy water.
Too late.
Hydrate or dihydrate.
Oh no. Q2, e to the minus, I, H bar, delta T, Q1. All right, so now let's take a look at this guy. This is just one specific one, namely it's the one to the left of this. Okay, so it's this one that's supposed to be right here. There's an expansion that we're gonna need. It's called the Campbell, I'm probably just gonna say it. It's CBH expansion, or CBH formula, or the Campbell-Baker-Hausdorff formula. Okay. Again, all of my notes on this are in Discord, so if you'd like to see all this stuff written down, you can head into Discord for that. And this formula is simple. It goes like this. If you have an exponential, the exponent of a plus b is equal to a couple things. It's equal to, I think these are operators too, by the way. I think.
But how does this apply to time?
What, do you have to go back to work? You too. Have a great day at work, NC. This will be on, like I said, the VOD will be up if you're interested. These QIs are projection operators, and if you take a vector and project it onto its basis vector and add everything up, you'll get back to where you started with. So the sum of the projector operators is the identity operator. Right, the sum of the projection operators is sure, but if you integrate, it's just one. So the sum it's true. Are these position operator eigenstates or energy eigenstates? These are all position. Position. Okay. I don't think we're in disagreement, Pretz. I think you are agreeing. Okay, so let's keep going. So we need the Campbell, Baker, and Hausdorff formula. Exponent of A plus B is going to be exponent of A times exponent of B times the exponent. Now these are operators, right? So they behave a little differently. I'm pretty sure they're operators. Someone correct me if that's wrong, but I'm almost... Otherwise, it wouldn't make sense to keep going with this, right? The commutator AB plus, and then you can just expand that stuff. It's gonna get smaller and smaller, so we're not too concerned about it, right? Because that means that we can take the following expression. How awkward is this? Ugh. Take a knee, everyone. You'll see why, too. Something very nice happens. Something very nice, and maybe if you've never seen path integration, this is pretty unexpected. So exp, the exponent, we can take a look at this guy. I, Hamiltonian, delta t, is going to be equal to, remember our Hamiltonian is equal to 1 over 2m, operator p squared plus the potential. And this is going to be what we get then. We'll get the exponent of, and since this h can be split into those two terms, the p squared plus the q squared term, we can do the exponent of negative I, and then this delta t over 2m. So again, here we go with this, the I, the delta t, and then, you know, the 1 over 2m times the operator p squared. And then we're going to add that to the potential term, or in the CBH formula, we're going to multiply the exp, negative I, delta t, times that potential term, which is just a function of the potential. Now, what does this mean for the rest of it? This just means that we have some higher order terms. Now, these truly are higher order terms. We don't really need to worry about them because they will... the nature of this, they're higher order terms in dt, and that's obviously very small. We're sending that to 0, and you're going to end up getting a dt squared and beyond with that. So we're going to not worry about that stuff because it's, again, too small to matter. I guess the CBH, I think the CBH is for, this is for operators, so matrices in general. it'll hold. All right, so this is where we're at. We've split up this into these following things, which is going to be very helpful when we need to move on to the next section. So let's keep going. We are making all right time. I'm also getting new chalk. If Professor Peter comes in, let me know. I think I got Hagamoro chalk, which I'm pretty excited about, but I thought that was discontinued, and it was like all over Amazon again. So did someone buy Hagamoro and is remaking it? Does anyone know that? I feel like Professor Peter and the boring math professor were the two who were talking about it with me last, and maybe Dr. Young as well. So what is our, remember we were looking at that one amplitude, so what does it look like now? And we can write it down. Q2, if this is just, again, the one amplitude. We're only looking at this little guy right here. And we're going to evaluate what happens. Well, we're going to add another completeness theorem. Remember, we can do that, but this time we're going to do it with momentum. So we're going to add, one momentum in. And this is what it's going to look like. We'll have e to the I delta t over 2m. We are applying two things. We are going to add a completeness, and we're also going to do that CBH formula. Operator p squared, p1. This is the p1. I'm not gonna have enough room, am I? E to the negative I delta t times v q operator q1. Is that it? I think that's it. It's a little squish there. But anyway, so you can see that we can split this up like the doing CBH, and we'll slip this this completeness theorem in, right? And what can we do with this? Well, these are operators, so we can do the whole Taylor expansion, apply the operators, and then go back up into Taylor expansion thing. It's a very useful tool. Maybe some might say too useful, but when we do that, we'll get dp, and we can actually pull out some eigenvalues, right? E to the negative I. So we're going to, again, unpack this in a Taylor series, apply the operators to the states, get the eigenvalues out, and then put this back up into an exponential value, and it will look like this. Negative I times delta t over 2m, p1 squared, where p1 is the eigenvalue of the eigenvector p1, or eigenstate, to be clear, vq1, where q1 is the eigenvalue of the q1 state. So now we have q2. Oh, jeez, there's a bug. q2, p1, p1, q1. You don't even need CBH, you can use. Nice. Nice, sure. Nice. Okay, cool. All right, so I think the CBH is kind of just like a general one, but I think what Admiral Entropy is doing is specific to our case, which is really cool as well. All right, now we have this done. Looks good. We can do this. Do you guys remember this old trick where we had, if you had Q here and a P here, right, is equal to 2 pi. What's this? I mean, we just did it. It looks a little different. IPQ. What? Do you guys remember what that is? And like I said, we just did it. It has a different thing. I think this is where Admiral Entropy's question comes into play in Discord. Maybe not yet. Very soon here. But this is the Dirac Delta. right? Like we can make a Dirac Delta by using this. And we did that before, and it was not long ago. I think it was in the Green's function. It's probably the best way to look, so if you're kind of curious about that, you can go check out the VOD on Green's function. I think I highlighted it, so it's not going to go anywhere anytime soon. But it is not on YouTube, it is on the Twitch channel. So let's rewrite this again. Now we're going to take all of our eigenfunctions out front. E to the negative I delta t with our q eigenfunction. And now we're going to have e to the I p1 q2 minus q1. And this is where the first inkling of something odd has happened. What's odd about this particular function? Okay, so this, if you haven't realized yet, I have removed all of the quantum from this, right? We have applied all of our eigenstates, we've done all our measurements on the eigensystem, on the eigenstates, and gotten eigenvalues for it, and then put it into a classical style Hamiltonian. So we can actually rewrite this as dp1 over 2 pi, where these 2 pi has now come from this factor over here, if you're trying to figure out where this is. And we have e to the minus I h, and we have a classical Hamiltonian p1 q1 delta t e to the I p1 times this propagator looking like thing. And there we are. So, but yeah, so this is where we're at. We have this, we've gone from something very highly quantum to something that looks pretty classical, right? But now we just have to extend it from having just an infinitesimally small piece of this to the whole chain, right? So it doesn't work like that. And the one thing is I know that people have been kind of getting hung up a little bit on some of the stuff, like what type of Hamiltonian we're using and everything like that. This is just a general example of a Hamiltonian, the one I gave you, where you have the p squared and the q, or the p squared and the q squared, or the q, excuse me. But there's also other ones you can do, and there's kind of a simple formalism for handling it. And rewriting a quantum Hamiltonian as classical is done with what's called Weil ordering, which I know very little about. But it's basically the following. You take the Hamiltonian of some p and q operator, and you can define it as a huge mess of an integral, but I'll show you what it looks like. Nevertheless, it's not going to be very relevant for what we do right now. However, if you ever wanted to evaluate your own Hamiltonian, this might be a way to do it. I don't know all of the stipulations for what this works for and what it doesn't work for. But a general way to get a quantum Hamiltonian as a classical Hamiltonian looks like this. Am I going into chat? No, I can go above chat. At least now I am aware of the situation. Oh, I've lost it. There it is. And it kind of looks a little bit like a Fourier transform, right? Is this not a Fourier transform? I'm just a little bit confused. Most texts just gloss over this whole issue, which only matters if the Hamiltonian has terms with p and q multiplied. Yeah. But it kind of looks like a Fourier transform, right? Does it not look like a Fourier transform? I don't know. It kind of looks like that to me. Interesting to know, Admiral Entropy says that most textbooks just gloss over this, unless you have p's and q's multiplied. I don't know. I'm not sure. But nevertheless, we won't worry about it too much. Our Hamiltonian will do the job just fine for a lot of this stuff, as it does in most situations. But what does that mean? That means we have a couple things, we have a couple flaws. We can generalize this a little more by taking this term right here and changing it. And what we have to change it into is just a q bar 1, which is going to be equal to 1/2 q1 plus q2. And this is going to be added into our Hamiltonian to make things nicer. Anna Kim Luke, welcome to the channel. If you have any questions, !ask and then your question, and I will answer it as soon as I get a chance. For now, we're finishing up. We're pretty close to being done with today's lesson. Now this exchange, which is going to go into our Hamiltonian in a little while, will only it will have no difference, makes no difference in our specific situation of having our minuscule d go to 0. Okay? So, this is the fun part. Now we get to rewrite our overall amplitude using the stuff that we've done here, right? We've found this one tiny piece of the amplitude, this little tiny puzzle piece, right? You know, this even infinitesimally small puzzle piece right here, and we figured out what the amplitude is for it to go, for a particle to go from here to here, and now we can go ahead and extend this to the whole thing.
Minuscule d.
Very random, but how much did your blackboard cost approximately? This is actually just drywall with blackboard paint. So overall, I think it was maybe 20 bucks. It was also 4 years ago, so I'm having trouble recalling. But it's a standard 4x8 piece of drywall. I put blackboard paint on, and then I covered it with, I put caps on the end. Yeah, it was actually really, really easy. Who drew the top left pony? A true masterpiece. Pony is the mascot of this channel. We love our pony. It's very nice. You always know exactly what it is because it says so right here. It's a very nice pony. Alright, so now we're going to re-look at our entire amplitude to see if we can make sense of breaking it into these smaller pieces. So let's rewrite it. We'll rewrite it in what we've gotten so far with the q bar instead of the q, to sort of account for maybe like a slightly more, or maybe a less trivial, you know, Hamiltonian. And we get the product, the integral of the product of all of our dqk's, but now we also have added another completeness, which is our momentum. So we have dp j over 2 pi. Remember, we added this one in. It's not a potato. Definitely not a potato, because it says pony. Then we have e to the I, pi. We get that propagator term, qj plus 1 minus qj. And then we have lastly our e to the negative I. And then we have some Hamiltonian of p, j, and then q bar j, delta t. Now, I don't know about you guys, but I don't really want to keep evaluating things that look like this. This is really, really long. And we still don't really have any clear intuition of what this stuff is. Like, the Hamiltonian, sure, it's the sum of all the energy to get from here to here. We have our infinitesimal small pieces, but we're still dealing with an integration over now 2 variables, because we've added 2 completeness relations, and it's getting longer and more complicated when you really think about it. So, doing all of this stuff, maybe I should mention at this point that we have boundary conditions, obviously, of Q0, or Q initial. What is that? What am I going to call it? Q0 is equal to Q prime, and Q n plus 1 is equal to Q double prime. Okay. So we can do one more thing. We can talk about the change, maybe like a Q dot, how Q changes with time. We're going to define it to be you know, we're going to take any 2 Q's, it doesn't matter. So Qj plus 1 minus Qj, or Qj, right? And we're going to divide that by delta t. So pick any two q's that are next to each other. This one and this one, you know, this one and this one, whatever two q's. You're going to subtract them, so now you have the distance between the two, and you're going to divide it by this infinitesimally small time. And this is basically going to tell you how much q changes per unit of time for this particular case, with the limit, you know, limit as delta q goes to 0. Now we get to our very interesting notation that I'm sure many of you have seen, and if you were like me when I was in undergrad, I always wondered what this meant, but I could never figure it out. I have a better idea of what it means now, but I realized that most people just don't know what it means. Like really, truly, physically don't know what it means. But it's the integral over all paths of dq, the integral over all paths of dp, or d momentum, I think it's a p. Exponent now of I, and now we're in the exponent, and we're going to do the integral from t to t double prime dt, where we're really just sort of taking this stuff right here and kind of turning it into, where am I? Have I lost it? Oh, no, here we go. So we have p, and then the delta q, and then we have, h times p, or h, just the h, there we go, h. Okay, so we're taking this integral, exponent of the integral, integrating over time, and we get something that looks like this. Again, remember, we're in the exponent, so p of t, q dot of t, minus h of p t qt. Cutie! Okay. The site link is broken? Really? That's a bummer. I'll take a look at that in just a minute. Thank you for letting me know, Anakin. I appreciate that. Okay, so now we have the exponent stuff. We've taken all this stuff and we've put it underneath an integral over time. Why? Well, because, you know, remember this is the Heisenberg, and these actually can be written as time dependence. And also we want to look at it like this way for a very specific reason. We want it to be in this form for something very, very specific. And that is the following. Now, if p and q, if the Hamiltonian, excuse me, is quadratic in p, which ours is quadratic in p, we know that, then what is special about the integral of the Hamiltonian part of p? It's Gaussian, right? So anytime we get an integral of a Gaussian, we can go ahead and we have the exponent with p squared in the numerator, or p squared in the exponent, excuse me. So that means that we can take Gaussian and we can absorb the Gaussian into here. So what does that mean? If for us, that means we can rewrite this. I know this is a little bit ad hoc for some people if you don't realize it right away, but if you play around with it a few times, I think you'll see it. That Hamiltonian is dependent on p squared, so you can take the integral with respect to, you know, dp, the integral over all paths, and you can get a Gaussian, which will be then absorbed into that term right there, okay? Because remember, it's just a constant. The integral of a Gaussian is just a constant. So, and again, this d, if you're unsure, it's just the integral over all of these paths. You just pick a path. It's the integral over all of them. So we're considering every single path possible in phase space. And what does that mean in phase space? That just means that it has to be physically possible. It's the best way that I could think of it. Does anybody have a good way to say what this is? This is what I've always thought. Like, it's, you know, over all of the paths in phase space, where phase space is sort of limiting to things that are actually physical. But maybe somebody has a better explanation of that. But what happens when we do this? Well, when we do this, it gives us a final form. This should look familiar to many people, right? If you've done classical mechanics above a certain level, like maybe, I don't know, it's sophomore or junior level classical mechanics. I don't know. It depends on your school, I suppose. Mine was junior, I think. And we'll get q double prime t, so we're going back to our original amplitude, this guy right here, and now we're going to rewrite this in our pretty much our final form of consideration. Exponent, the integral over all of the q's, exponent of I times the integral of t prime to t double prime, right? And that chalk is gone forever. And we get dt times this, our friend, the Lagrangian. Right? Now, notice something about this. How did we eliminate the rest of the p's? Because there's still p's there, right? Well, if anybody is remembering their Lagrangian mechanics, they can remember the following thing. You can find a stationary point of p. So let's say 0 is equal to, the partial with respect to p of that term right there that's underlined. You'll get p q dot minus h p q. Now remember that, so this is going to be, remember this is equal to 0, right? And then this is going to equal q dot minus the derivative of h p of q with respect to p. Remember rp, I wrote q in my notes, but I'm pretty sure it's supposed to be p. Yeah, it's definitely p. Remember, p is only quadratic, which means if it's quadratic, then there's only going to be a single p left. Since it's equal to 0, you can solve for that p. You can take that, whatever is left, plug it back into whatever p is left over there, and you can get a Lagrangian that is only dependent on q. So with this, you solve for p, plug it back into whatever you have here, and you get your Lagrangian that is fully dependent on only a q. So now, let's walk through what we did again. We have our final form for the matrix, or for the path integral. Yeah, so this is it. And I think the phases is just sort of my way of explaining about like how it has to be physical. But what we did was we started with a Hamiltonian, right? We understood what the Hamiltonian was from quantum mechanics. We applied our amplitude like we would under normal circumstances in quantum mechanics, where we have, IH times delta t, sandwiched between a final state and an initial state. And then we used two completeness theorems to get into, something else. And by doing so, we were able to take it out of the quantum and into the classical, where we actually were dealing with a classical Hamiltonian, which I think is one of the big beauties and surprises of path integration. It's all classical. After you get to a certain step, it goes into a classical arrangement. And then with the classical arrangement done, we still had kind of a monstrosity because we were into two variables, which made it very complicated, and 3 if you count time. And so you have position, momentum, and time, and you know that those won't work together, but you can use your classical Lagrangians and Hamiltonians formalism, right, from going from a Hamiltonian to a Lagrangian, to get out the p and then get into a single variable of q, which depends on t. And then the integral is really what takes it. So this is, does anyone know what the integral from t prime to t double prime of the Lagrangian is? Yeah. It's the action, Admiral Entropy, very good. So we got the action, which makes perfect sense, right? Because all of this was done to get this Lagrangian, right? Which is just the action from this particle to this particle in a classical setting, right? The only difference is, the weird thing is like what you're finding is a probability amplitude that it's going to follow any one of these specific paths, right? And I think that's the hard part, is finding a probability amplitude that you're actually going to go this one, or 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 like this one if it's possible. You know, like what is the actual path that you take? Well, you're really just finding a probability amplitude that you'll take a single path. And that's the hard part because this is all classical, so we don't exactly have a good intuition of what that is.